Hello, my name is Eleni Economidou and I'm a PhD candidate at the Center for Human-Computer Interaction of the University of Salzburg. This is a video presentation of our pictorial audio frequency induction loops as a design material for architecture interactivity. An illustrated guide. I will be presenting on behalf of my co-authors Bart, Moritz, Alina, Martin and Manfred. The story of the sound of space starts in 2018 when we first got in contact with the architect of an integration school for deaf, hard of hearing and hearing students and staff. We have indefinitely deployed 3 research products at the school's entrance hall. In this pictorial, we focus on the sound of space, the interactive soundscape installation based on 3 overlapping audio frequency induction loops. We contribute design knowledge on the novel use of audio induction loops as a material for architecture interactivity and learnings from our design process. The final system consists of the overlapping loop configuration placed under the floor, a cochlear implant, hearing aid or a tangible receiver, and a stand containing the hardware and charging pad for the tangible. We followed the illustrated design process. First, we gathered requirements from the stakeholders. We researched and analyzed audio loops functionality and their layouts. We went on designing the interaction and developing scenarios of use. We ideated on alternative typologies and tinkered with their functionality. To settle on a typology, we built one-to-one mockups for testing. Finally, we implemented all components on site and performed some further tests to settle on the audio files. We drew inspiration from sensory augmentation, focusing on people with cochlear implants or hearing aids, by visualizing, emphasizing, and complementing their ability to pick electromagnetic signals through their device. The T setting, which stands for TELECOIL, is a built-in feature of most cochlear implants and hearing aids. This T switch turns off the microphone and activates the tiny iron core coil inductor that functions as an antenna. In short, it picks up electromagnetic field signals and converts them into sound. The TELECOIL can receive audio signals emitted by audio frequency induction loops. These loops are usually made out of copper tape wires that carry audio frequency provided by an amplifier. The audio frequency induction loops, usually found in lecture rooms, museums, and public transport, are typically installed at the perimeter of a room, under the final layer of the floor construction. The magnetic field is consistent within the looped area, but slips out of it. In the sound of space, visitors can experience the generated soundscape by walking through the space and holding a tangible receiver or wearing a cochlear implant or a hearing aid. Its aim is to raise awareness about the unique constellation of the school's population. Each of the installations in the space reveals an aspect of the riddle. For example, one such riddle is: deaf people sign when they dream, as a form of sleep talking. The word sleep is translated into snoring sounds and broadcast in an area where the induction loops overlap. In other overlapping areas, the word sleep is broadcast. Sounds of chatter mask the clues in the rest of the areas. The sound of space can be experienced through various positions, like lying, kneeling, stretching, or walking in space. The received amplitude depends on the orientation of the coil with respect to the magnetic field. The closer the receiver is to the floor and the field, the higher the amplitude of the sound. For example, a child may experience a louder soundscape than an adult. Since the magnetic fields are proportional to the audio signals, signal interference can be used deliberately to amplify, cancel out, combine, or subtract source signals in the overlapping areas. The combination of multiple audio induction loops allows operating these at different topologies. In our design, we purposefully hide an audio part of the riddle in the mixed signals. To achieve this concealment effect, we use subtraction where inverse signals cancel each other out, as seen here in the fourth schematic. Using 3 or more loops results in complex combinations of these topologies. From the experience perspective, the field is quite evenly distributed, which means that moving the receiver through the soundscape results in a fade. Rotating the TELECOIL perpendicularly to a loop makes the audio signal fade from full amplitude to 0. we performed in-house tests using loops, a signal receiver, and a wireless speaker to test the topologies and find the most optimal solution for covering as much space possible and maximum overlaps with the least amount of audio loops. For the on-site implementation, we drew the final topology on the building plan. The electrician of the school laid the flat copper tapes before the final layer of the floor was placed on top. All active components were placed in a custom-built metal enclosure. We performed further tests using a receiver to make sure everything worked as intended. One way of experiencing the soundscape is through the tangible, a handheld receiver device. Its components are mainly parts of an off-the-shelf TELECOIL receiver module. We removed the casing of the receiver module, replaced the battery supply with a rechargeable battery system consisting of an induction pad set. A charging regulator module and a voltage regulator control the charging and the voltage. A small speaker is used to sonify the electromagnetic field signals. Through open-ended exploration and experimental engineering, we discovered that audio induction loop systems are robust, cost-effective, with extensive documentation on their use. They have an always-on state and a unidirectional experience with novel and surprising interactions potential. They provide seamless coupling of input and output and virtually unlimited resolution with simple infrastructure. Designing with electromagnetism facilitates in interaction ambiguity, as it generates fields that are invisible. It is essentially a technology that awaits to be explored, reconfigured, and recontextualized. As far as pitfalls go, there is no precedent of making use of audio frequency induction loops as a design material. Therefore, there is a risk of investing too much time and resources. It also requires a lot of trial and error efforts in the process. Limiting factors of this type of systems are the hard-to-predict soundscapes due to the way that electromagnetic fields propagate and the possibility of unwanted interference with other signals. Our system uses assistive technology to enable hearing people to experience what people with hearing aids or cochlear implants are able to experience. Sharing similarities with ability-based design, the sound of space is tailored to the abilities of the people using it. As an allegory, the tangible represents a hearing aid or a cochlear implant that picks up electromagnetic signals as an attempt to look at the wearers as transhumans. Strictly speaking, a cochlear implant is not only a neural prosthesis that allows the substitution of a sensory organ, but it also can pick ultrasonic sounds and electromagnetic signals. We see both research and design opportunities arising when it comes to designing for this subgroup and seeing assistive devices as support devices for a transhuman ability. One of our systems highlights the instant coupling of input and output gives the illusion of physical form to digital information, a key characteristic of tangible user interfaces. Therefore, we view our tangible device functioning as one when experiencing the soundscape. We would like to call for a neighboring definition for experiential tangible user interfaces that frames devices that appear as tangible user interfaces on an experiential level but do not adhere per se to a computational model. To conclude, we made use of audio loops as a design material for architectural interactivity. To achieve this, close collaboration with consultants and construction experts was essential to ensure the smooth operation of the system. Testing the topologies at a one-to-one scale and visiting the construction site to get a feel of the space before the implementation was necessary to calibrate the shape, size, and type of the audio loop topology. Thank you to everyone who was part of the Sound of Space journey, and thank you for watching.